In this video, we're going to work example problems where we solve triangles using the law of sines. Now, when it comes to using the law of sines to solve triangles, there's two cases where the law of sines is applicable. The first case is the most straightforward, where you know two angles and a side length, but whether or not that side length is included between the two angles doesn't matter, because once you have two angles, you can automatically solve for the third angle. So the side length is anywhere you want it to be relative to the angles. And with that, you can use the law of sines to find any of the other side lengths. And then you can use the law of sines again to find the third side length. And so for example, here we've got two angles and a side length, but since we have two angles, we automatically can get the third angle. So we've really got three angles and a side length. And what's nice about this case is that this is one of the cases where this follows from a congruence axiom, the side angle side congruence axiom. So once you specify two angles and a side length, this triangle is fully constrained to where there's no ambiguity. A can only be one number. This side length can only be one number. And this angle can only be one number. So that's why this case of the use of the law of sines is straightforward. But there's also the ambiguous case of the use of the law of sines when you've got two side lengths and an angle that's not included between those two side lengths. And the use of the law of sines for this case, we'll look into detail on this in the next section. But again, in this video, let's work some problems where we use the law of sines for its first case, which is the most straightforward case, again, where you've got two angles and a side length. But again, so you've got two angles, but that automatically means you've got the third angle as well. So let's get that third angle. You've got 75 plus 60, 135. So now 180 minus 135 is 45. Okay, now the law of sines, you should be able to memorize the law of sines. It states that if you take the ratio of the sine of any one of these angles, any one of the angles of the triangle, the ratio of that to the side length opposite that angle, then that's going to be a constant for all angle side length pairs. That's the idea. Again, the sine of any angle you want divided by the side length opposite of that angle, or you could do it in reverse. You could say the side length, any side length you want divided by the sine of the angle opposite that side length is equal to, and then just pick another pair and do the same thing. You just keep it consistent. If you put the side length in the numerator or in the sine of the angle in the denominator, then just keep that consistent. You could do it in any order you want, but that's constant for any angle side length pair. So, okay, here we want to solve for just side length A. We're not going to solve these entire triangles, but we could. But let's solve for side length A. So, okay, so we need A. Now, divided by what? The sine of the angle opposite of that side is equal to, now just pick any other angle side length pair. Just be consistent. So we want to pick this pair with side C and angle C because we have side C. So be consistent. We're not going to put the sine of 45 in the numerator because we want to be consistent with what we did over here. So root 2 over, and then sine of the angle opposite that. Okay, so now sine of 60 and sine of 45, we can use the 30, 60, 90, and 45, 45, 90 reference triangles. Okay. So 1, 1, square root of 2, 1, root 3, 2. All right, so sine of 60 we can see is root 3 over 2. Okay, then we got root 2 over sine of 45 is 1 over root 2. So let's see, it's 2a over root 3 is equal to, and this is going to be root 2 times root 2 is just 2. So we've got 2a is equal to 2 root 3 divide both sides by 2. So you've got a is equal to root 3. It's nice and straightforward. There's no ambiguity. All we did was take the sign of a number, the sign of two numbers. Well, the sign function is, there's no ambiguity there, right? The ambiguity with the law of signs comes into play with, to solve for an unknown angle, you have to take the inverse sine of both sides of the equation, so there's ambiguity there. Now you might say, well, doesn't this come into play with the law of cosines as well? No, it actually doesn't. There's only one situation with solving oblique triangles that's ambiguous, and that's what the law of sines for the second case. Okay, so here we've got, you see, two angles and a side length. But again, you might say, okay, well, does the side length need to be included between the two angles? It doesn't matter, because let's say we had this side length instead. Well, that's not included between the two angles, but we've got two angles. We can get the third angle, so we can arrange it however we want. So, like, in other words, the angle side angle is the congruence axiom. It's one of the congruence axioms. But you could say, if we had, so this is angle side angle, but let's say we had this side length instead. So that means we have angle side, but it doesn't matter because we can get the third angle anyway, and we have angle side angle anyway. So, okay. 105 plus 45 is 150. 180 minus 150 is 30. Okay, so we want to get side length A, so we'll do A over sine of 45. We could have done sine of 45 in the numerator, but I think it makes it a little bit easier to solve for A. The cross multiplying a little bit easier, but it doesn't matter. A over sine of 45, and then we'll do 10 over sine of 30. Okay. So sine of 45 we saw was 1 over root 2. Okay, and then sine of 30 is, we can see, is 1/2. Okay, 1/2. So, all right, A root 2 is equal to 20. All right, now let's rationalize this. So we've got A is equal to 20 root 2 divided by 2. So A is equal to 10 root 2. Okay, so now here we want to solve the entire triangle. So we've got side length A we want to find, side length B we want to find, and angle C. So we can start by just getting angle C. We've got two angles and a side length. So let's get angle C. A plus 7 is 15. But now we need to subtract this from 180. .95. So this is 95 degrees. Okay, so let's do sine of 95 over 18 is equal to, and now we just pick either one of these. So let's do sine of 37 over A. So cross multiplying, A sine of 95 is equal to 18 sine of 37. So A is equal to 18 sine of 37 over sine of 95. So we'll use our calculator for this. We're in degree mode. Okay. Sine 95. 10.9 in meters. So, okay. Okay, now side length B. So, okay, we can technically we could use like do sine of 37 over 10.9 is equal to sine of 48 over b. But one good practice you can think about, you don't have to do this, I mean, but it's just good practice. The textbook mentioned this, but when at all possible, if you have a choice, then for like intermediate calculations, use what's given. So like you see, we could do sine of 37 over 10.9 is equal to sine of 48 over b and solve for b. Or we could do sine of 95 over 18 is equal to sine of 48 over b. Well, since we have a choice, let's use what's given, because this is like this. That's going to reduce the rounding errors. It really technically doesn't matter, but it's just something to think about. It's good practice. So we'll go ahead and say, all right, b over sine of 48 is equal to, and then 18 over sine of 95. So b sine of 95 is equal to 18 sine of 48. So b is equal to 18 sine of 48 over sine of 95. So 18, oh, well, I can use 18 sine of 48 over sine of 95. 13.4 meters. Okay, let's just start by getting the third angle. So 52 plus 29 is 81. Now 180 minus 81. So 180 minus 80 is 100. But then you have that extra one, so this is going to be 99 degrees. Okay, so we've got, let's see, this is side length C, side length B. So we've got side length C over the sine of 29 degrees is equal to then side length A over the sine of 99 degrees. So C sine of 99 is equal to 43 sine of 29. So C is equal to 43 sine of 29 over sine of 99. So C is equal to, all right, 43 sine 29 over sine of 99. There we go. 21.1 centimeters. Okay. All right, now, so again, let's use this pair here since that we were given the 43. So now we've got B over sine of 52 is equal to 43 over sine of 99. So B sine of 99 is equal to 43 sine of 52. So B is equal to 43 sine of 52 over sine of 99. All right, 43 sine of 52. That's 34.3 centimeters. Okay. All right, so now we've got these more precise angles. So let's see. let's get that third angle, 115.5. Add that to 27.2. So 7, 12, 142.7. Now let's subtract this from 180. So let's see, 7. All right, so 3, 9 minus 2 is 7. 7 minus 4 is 3. So this is 37.3 degrees. Okay, so we've got, let's see, this is side length A, side length B. So we've got sine of 27.2 degrees over side length A is equal to sine of 115.5 degrees over 76. So, okay, we can kind of do this in our heads here. We can see that A is going to be 76 sine of 27.2 degrees over sine of 115.5 degrees. So 76 sine of 27.2 divided by sine of 115.5 is 38.5 feet. Okay. All right, so now we've got, let's see, sine of 115.5 degrees over 76 is equal to sine of 37.3 over B. So we can see that B is going to be, you've got 76 divided by sine, so, okay, sine of 37.3, there we go, so 51.0 feet. Okay, let's find the third angle. So 124.1 plus 18.7. 7 plus 1 is 8. 8 plus 4 is 12. 2 plus 1 plus 1 is 4. 142.8. So 180.0 minus 1. We added these. 142.8. We want to subtract these. So let's see. 7. Okay, so 10 minus 8 is 2. 9 minus 2 is 7. 7 minus 4 is 3. 37.2 degrees. All right, this is side length A. This is side length C. So, okay. Sine of 124.1 degrees over side length C is equal to sine of 18.7 degrees over 94.6. So we can see that C is going to be 94.6 times sine of 124.1 degrees over sine of 18.7 degrees. Could you just cross multiply these? These are on one side, this times this on the other side, then you divide both sides by this. So C is equal to, all right, 94.6 times sine of 124.1 divided by sine of 18.7. 244.3 meters. Okay. Now, again, to get A, let's use what we're given. We'd rather do that if we can have a choice, but it's not that big of a deal if you use this, but it's just good practice. Okay, so sine of 18.7 degrees over 94.6 is equal to now sine of 37.2 degrees over A. So now let's do this cross multiplication and division in our head. We can see that A is equal to, okay, so 94.6 times sine of 37.2 divided by sine of 18.7, 178.4 meters. So, okay. All right. For these next problems, we want to find the area of the triangle. And we're going to use the area formula that was developed using trig functions, which is actually really cool. Because we know that the classic geometry area of a triangle is 1/2 times base times height. And it can be kind of, it's not that big of a deal, but it's, you have to think about what exactly the height is, right? You have to construct the height of the triangle and get the height. And then, you have to understand the relationship between the base and the height, because you can construct a perpendicular. Well, this is a right triangle. This is actually easy. 1/2 times, this is the height and this is the base. But something like this, they constructed the height for us, but, you have to, there's 3 different heights and bases. Here's another height and a base. Which, I mean, look, if the problem sets itself up that way and you can get the height and the base, that's fine. But it's pretty cool that with trigonometry, you have a formula for the area that's strictly based on the one angle and 2 side lengths of the triangle, not a height, not an ambiguous height. So with all you do is it's 1/2 times pick 2 side lengths, multiply them together, and then take the sine of the angle between those 2 side lengths you picked and multiply that as well. That's the area. And you can do this with any side length pair and angle between them that you want. So it's pretty cool. Now, in this case, again, with a right triangle, it's easy because, okay, we actually have the height is one of the side lengths of the triangle. So it actually works out to where if we did that trigonometry formula, if we did 1/2 times and then chose these 2 side lengths, well, this is already the base and the height, so we would expect the sine of the angle between those 2 side lengths to be 1, and it is. Again, because this is already the base times the height anyway. So, this formula for area with trig functions it's kind of it's not that useful when it comes to a right triangle because, again, you already have the base and height right in front of you. Okay, but like here, for example, I wish they wouldn't have constructed the heights for us because, when you're typically dealing with a triangle, you don't have the height right in front of you. Because, yeah, I mean, using the classic formula for the area of a triangle, just do 1/2 times 2 times √3. But, in typical situations, you don't have the height right in front of you. So if you didn't have the height right in front of you, you could, the trig function formula for area of a triangle is a lot more intuitive. You say 1/2, pick 2 side lengths. In this case, it doesn't matter because it's equilateral, but okay, these 2 side lengths. So 1/2 times 2 times 2 times the sine of the angle between those 2. And that's it. So let's see, 30, 60, 90. So you've got 2 times sine of 60 is √3 over 2, √3. Okay, again, I really wish they wouldn't have given us the height like this, because now it's easy. It's 1/2 times root 2 times 1. Okay, but you could, that base times height formula, you could also do this. Here's another height, 1/2 times 2 times that height. So, I mean, if it works out to where getting the height and the base of a triangle is straightforward, then I guess you can go ahead and use that. But let's say it was hard to get this height here. Well, then you just do 1/2, pick any two side lengths. Let's pick one and these two. So 1/2 times that side length times that side length times the sine of the angle between them, sine of 45. So we know sine of 45 is 1 over root 2. Now we can rationalize this. So area is equal to root 2 over 2. Okay, so area is equal to 1/2. Let's use these two side lengths. So 2 times root 2 times the sine of 45. So root 2 times sine of 45 is 1 over root 2. So the area is equal to 1.